Okay, we'll start now. Hello. So what we are discussing is about the dimensionality reduction technique. Right. In that sequence, we are discussing about this KLDA, right? Kernel LDA. You know what is dimensionality reduction? We know that PCA, right? The finding of direction of maximum variance, right? So this E1 and E2, which is in the E1 is basically in the direction of maximum variance. This is about this PCA, right? So we discussed that. We project that vector to that basis, right? So this is what the thing. And this fast computation we discussed, right? Of this PCA. Just recollect that we are actually finding out this V as the eigenvector for this covariance matrix CX, right? And the key point here is this eigenvector V can be represented as the product, right? M into U, where M is a matrix with the training data itself. X1, X2, X3, and so on up to this Xn, they are all the training data, right? What I really mean by this is, if I have a vector space with the training data as available in that space, right? So let us, yeah. So you have a vector space and your training data are available in that space, right? So it is like X1, X2, like that, you have something like Xn. They are all the training data available in that space. The idea is the eigenvector of the matrix Cx, which is, which we compute using the training data, right? Using this training data only, we compute this Cx as an estimate, right? So in pattern recognition terminology, we say that it's a scatter matrix. We know, I think we discussed all those things earlier, and just for the sake of completion, I'm telling that, right? So this eigenvector V of the Cx, so that is also in the same vector space. So this is the vector space here. Is a vector space, right? The space spanned by the training data, right? X1, X2, X3 up to this Xn. And this eigenvector is also available in that space, right? So that is what it means. V is written as M into U. By doing some linear combination like P1 into X1 plus P2 into X2 and so on up to this Pn into Xn, right? We do this linear combination, and this U is basically this vector, right? So this is P1, P2, and so on up to this Pn, right? So M into U, we do the linear combination of this vector x1, x2, x3, and so on. This is a scalars here, P1, P2. By doing this linear combination, we get this eigenvector. This is the key point in this. So other things are straightforward, right? So V is represented as MU. This is the key point in it. Other things are straightforward, right? We are going to use this similar idea only for KLD. That is what I'm just recollecting, that this must be clear in it. You have to be clear in representing V equal to MU. So the eigenvector V can be represented as M into U. So that is the important point, right? Okay. Now coming to this KLD, right? So these things LDA we already discussed. So motivation behind this KLDA, right? So as you know, we have a vector which is in the feature dimension space, which is of size 2500 cross 1. We wanted this vector to be mapped to that lower dimension. Instead of mapping directly the vector to the lower dimension, what we do is we map to the higher dimension using some function phi. So this is mapping to the higher dimension, then bringing back to this lower dimension, right? Say for example y, right? So say this is going to be your 13 cross 1. So bringing to this higher dimension and then bringing to the lower dimension, right? We can actually do this. We can make this happen without really mapping to the higher dimension, without phi, without this function phi, right? So that is what we say that it is a kernel, right? Without really mapping to the higher dimension, but as if you know we do it in the higher dimension, we actually perform this KLDA in the higher dimension space. Right. So I'll just show you that. So the actual KLDA we are going to discuss now, the kernel trick. All right. So this is the important slide, kernel trick in KLDA. So what is that about? You have a vector, right? So this is very important from this slide onwards to understand about this KLDA, right? So this U is in the feature dimension space. By mapping this U to the higher dimension space using this function phi, we get a vector called V, right? Now we are going to compute the between class scatter matrix and within class scatter matrix using these vectors. Remember that they are all the vectors in the higher dimension space. Okay, you have to remember that. Now SBV, it is a between class scatter matrix using the vectors in the higher dimension, that is V here. And SWV is basically the within class scatter matrix using the vectors in the higher dimension space. So that is SWV, right? So now this V is the eigenvector satisfying this X. Basically, V is the eigenvectors of this form SW V inverse SBV V is eigenvector, which is equal to what? Lambda times this eigenvector. Instead of writing like this, we are writing this form. Nothing special in it, right? Okay, fine. Now, as usual, like what we did in PCA, fast PCA computation, the same trick we are going to use here. This is what the key point I already told, right? So we are going to replace this V with what? M into U, right? As you know that the eigenvector lies in the space spanned by the vectors used to compute matrices, right? So we have constructing this matrix M with all the vectors used, as a training data with all the classes. All the classes are arranged one after another, right? The first n1 vectors are in corresponding to class 1, and then the next n2 vectors class 2, and then n3 vectors, like that. They are arranged one after another. They are all the complete training data in the higher dimension space. Training data, right? In the higher dimension space. We are writing this V equal to MU, right? So now coming to this expression 2, we are writing SBV. In place of V, we are writing M into U, and here also having this M into U, and then multiplying M transpose on both sides, you are getting this M transpose SBV M is equal to lambda times M transpose SWV M, right? So this is the scatter matrix again. SBV is a scatter matrix using the vectors V, and this matrix, right? So of the inner product matrix. So I'll tell you that what is that about. So this is what we call it as this inner product matrix, right? So how that is constructed? You have, so you have that original vector u1 and you map to the higher dimension, and we get a vector v1, right? So this is that mapping from lower dimension to the high dimension using that function phi. Basically, V1 is nothing but phi of U1 here, right? So that is the expression what we are having, right? So now what we are doing here is we are computing this V1 transpose V1. Basically, this is nothing but phi of U1 transpose phi of U1 because V1 is phi of U1, right? So for example, if I consider this is basically phi of UN transpose phi of U2, right? So all this expression, whatever is there in this inner product matrix, using the vectors in the higher dimension space, all are inner product values. So as a kernel trick, what we do is, instead of having that function phi explicitly, we define the kernel function. This is important. This is what the kernel trick is all about. So I have a function called k of, so let me write like this, k of u1 comma, or make it as more general, ui comma uj, right? So this is basically the inner product of the corresponding vectors in the higher dimension space, right? Which I can define in the function called the kernel, which is what we call it as the kernel function. So in other words, this matrix I can be represented using that kernel function instead of using v1 v2, right? I can represent this one like this. The inner product matrix can also be written like this, k of u1 comma u1, it is like that, and here it is k of u1 comma un here, and it goes like this, and this is k of un comma u1, and it goes in this way, and this is k of un comma un. So you see that the inner product matrix now replaced with the kernel function, because you are actually vectors in the higher dimension, we are writing like this. And most important point here is, if I find out the scatter matrix, right, using this inner product matrix, the first, see what is the size of this? This size of this one is going to be the n cross n, right? Where this n is basically, say for example, if I'm having only 3 class, so it is like n1 plus n2 plus n3, right? So it means that the matrix what you get is of size n cross n, right? So n1 is the number of vectors in class 1 and n2 is the number of vectors in class 2, n3 is the number of vectors in class 3, right? So now what you do is you treat the first n1 vectors in this first n1 column, both are same only, here or here. First n1 columns you treat it as belonging to class 1. I have written here, first n1 columns of the matrix can be viewed as belonging to class 1, followed by n2 columns belonging to class 2, and so on. It goes like that. Suppose that if I have only 3 class, and the next n3 columns you treat it as what? Class 3. If I have only class 3, right? It is like that. So if I do that, this SBV is the between class scatter matrix belonging, right, with the vectors, the raw vectors, right? Of course, after mapping to the high dimension, like v1, v2, v3, and so on. That is the thing, right? So SBV is the between class scatter matrix, and using the vectors in the higher dimension space. What is there in the higher dimension space? Right? So these are all the vectors in the higher dimension space. v1, v2, v3, and so on, and vn1 plus n2 plus n3. So because there are n1 plus n2 plus n3 number of vectors totally available, using these vectors, if I find out this between class scatter matrix, that is going to be your SBV. And for the same vector, right, of course, remember that always the first n1 vectors we are treating as the vectors belonging to class 1, and the next n2 vectors belonging to class 2, and the next n3 vectors are belonging to class right? You know the expression what we discussed in LDA, so I don't want to write that expression. We know that how to compute this between class scatter matrix and within class scatter matrix if you are given a indexed class data. So using this data, if I find out this between class scatter matrix, let us represent that it is what? SBV. If I compute this between class scatter matrix using this data, let me call that as SWV, then M transpose SBVM and M transpose SWVM. If they are going to be the between class scatter matrix and within class scatter using the columns of this matrix I. Using the columns of the matrix I. Got it? So now, but using this PCA, we understand that we can actually find out this eigenvector, right, by computing M transpose SBVM. We need not actually compute this M transpose SBVM. Instead, we actually compute this matrix I here, and directly we can compute, if I find out this between class scatter matrix using this column vectors here, directly we can get a value for M transpose SBVM. Remember that we are not computing SB, right? So instead, we can actually do this one by computing the between class scatter matrix using the matrix I, that itself. So this is the between class scatter matrix using this vector I, right? Similarly, M transpose SWVM. This is the within class scatter matrix computed using this matrix I, right? So once that is known, we know the relationship, which is obvious, just like what we used it in PCA, right? So as I told you, this is the matrix I written using the kernel function. So here, this is what I am trying to say. So we call this M transpose SBVM as SB5 and M transpose SWVM as SW5. Remember that they are all the between class scatter matrix and within class scatter matrix computed using the inner product matrix I. Using this inner product matrix I, we can actually find out the between class scatter matrix and within class scatter matrix as SB5 and SW5, like that, so like this. So now you see, if I find out this eigenvector using this basis, so it means that you are actually finding out the between class scatter matrix and within class scatter matrix using the vectors of the inner product matrix I. For that, you can actually finding the eigenvector E satisfying the expression like this: SB phi E equal to lambda times SW phi E, like that. Now you know that this eigenvector E is related to the eigenvector Z, which is actually SBV, SWV, right? So this is the eigenvector. Z is basically the eigenvector, right, computed in the higher dimensional space, because SBV and SWV, they are all the between class scatter matrix and within class scatter matrix computed using the vectors in the higher dimensional space, right? So our goal is actually to get Z, but you see that the trick is helping. We can actually computing what? We are computing this E. Once E is known, then Z can be computed just by equating M into E. That is the trick. We don't want actually Z to be computed. If I want to have Z to be computed, we need V1, V2, V3 and so on, where V1 is nothing but phi of U1, where in further we need this basis function, this phi, the transfer function which map the vector lower dimension to the higher dimension. This is ruled out. So this is the difficult job. I don't want this phi explicitly. Phi I don't want. And hence we use the trick. We compute E. That is comfortable because this is computed using the inner product matrix. So I can compute this E. So once E is known, then I can compute this Z. So once Z is known, then the projection will come, right? So once this eigenvector E is known, right, we can actually find out these eigenvectors. Let us consider the projection with only one eigenvector, but the method is common for the other eigenvectors. The procedure is the same as that of the PCA LDA. What we do is we compute these eigenvectors, isn't it? We compute these eigenvectors, right? So for example, Z1, Z2, and so on, corresponding to the largest eigenvalue, and we project the vector using these eigenvectors. That is what we do, no? In PCA as well as LDA also we do the same thing. So like that, here we are actually finding out this vector Z equal to M into E, right? We find E and then we compute this Z. How the projection is going to happen? You have an arbitrary vector in the feature dimension space as usual, right? We have to map to the higher dimension, which using what? Phi of x. You may wonder, now we need this function phi in this expression. The idea is it is not needed. It is not needed. You see how that is going to happen. It is not needed. But this is the procedure. We need to map to the higher dimension. So we have this phi of x. Then we need to map. Mapping means Z transpose phi of x. Z transpose phi of x. That is the projection to this vector, right? And Z is nothing but M into E. So M into E, the whole transpose phi of x. So E transpose M transpose phi of x. What is more interesting is this part. M transpose phi of x is the interesting point. What is it? M transpose phi of x. You know, M is nothing but V1, V2, and so on up to this Vn1 plus N2 plus N3 here. And this V1 is actually the vector in the higher dimension, which is phi of x1, phi of x2, and so on. And it is going to be that phi of x n1 plus n2 plus n3 here. Now you are M transpose phi of x. So what is doing? M transpose is basically phi of x1 transpose, phi of x2 transpose. It goes like that, and this is phi of x n1 plus n2 plus n3 transpose here, and that is multiplied with what? Phi of x here, which is row and column. If you multiply, which is basically phi of x1 transpose phi of x, right? Phi of x2 transpose phi of x. It goes in that way. It is phi of x n1 plus n2 plus n3, the whole transpose phi of x. You see that again it is in the form of a inner product. That is the interesting point. We really don't need to have the function phi. This can be replaced with what? K of x1 comma x, and this can be written as k of x n1 plus n2 plus n3 comma x. We can write like that, isn't it? This is the interesting point. Even though I told in the previous slide, right, you need to compute this phi of x, but when you see this expression, it actually reveals that you don't really need to do it. Again, you need to have a, and that is what we say that it is a kernel trick. Kernel trick doesn't need phi, it needs only k. So we are able to do that. And mostly used kernel function is the Gaussian kernel function, which is actually given to you for reference here, right? So here, of course, we have one more tuning parameter, S square, is available that needs to be tuned properly, right, to do this task, right? So this is what we say that it is kernel LDA. Any questions before we continue? So